how drugs work, we have to go through a few other processes within the body. We're going to talk a little bit about general nerve transmission. How does the body send signals around, okay? And then we'll talk about it in general, and then we'll talk about where drugs insert themselves into that process, all right? And we know about receptors. You're all sitting there with a drug in front of you, caffeine, right? A lot of you. We have caffeine receptors in our body. Did you ever get like partway through a morning, like, where am I? And then you realize that you never like made yourself a cup of coffee or something? Although I open my eyes and I think coffee is the only thing that gets me out of bed, right? So we actually have caffeine receptors. We have nicotine receptors. That's why people are addicted, okay? We have cannabinoid receptors. You know what a cannabinoid is? Marijuana, yes. Okay, we have receptors in our body because we have substances in our bodies that act like those things. Yes?
So, like, say us, everyone, do we think our body just needs it, or for coffee?
There are physiological and psychological dependencies, right?
Yeah.
And if you don't have coffee and your body is used to it, the caffeine receptors are saying, okay, and you can get a headache. Has anybody ever gotten a caffeine headache? Yes. You're not making it up, okay? And we need it psychologically and physically, all right? Then we're going to talk about agonists and antagonists, okay? Drugs can act like agonists and antagonists. What does that mean, okay? Mechanism of action, how drugs work. This is really important. Drugs don't make you do something, your body do something it wouldn't normally do. It can make your brain do something it wouldn't normally do, okay? But it doesn't change your bodily processes. It doesn't do something, it doesn't impart a new function to your body, okay? It modulates what's happening within your body one way or another. It modulates the function of an organism, okay? They don't impart a new function to your organism. They can either produce the same action as an endogenous agent. Endogenous means what? Boring? No. Some of them are, you know what? Some of them are kind of boring, kind of background processes. What's endogenous mean?
Within, like a...
Within. An endogenous substance is something that your body produces. Okay? Does anybody ever heard of epinephrine?
Yes.
Do you know the other name for it?
Adrenaline.
Adrenaline.
Yeah.
Adrenaline and epinephrine are same thing. We know what adrenaline is, right? When you're taking your run in the morning, you need adrenaline, right? After you had your coffee, okay? Coffee doesn't make adrenaline, okay? So you need adrenaline, right? That's a good thing. Get your body pumping. Would you agree? It makes your heart pump faster. That's a good thing. You want to take your run. You need adrenaline, okay? What's in a local anesthetic? Epinephrine. So the epinephrine, which is good as your endogenous substance, giving you, the energy to run, okay, getting your heart beating faster. If you're sitting in a down chair and you're nervous as heck and somebody gives you epinephrine, okay, it can have that effect on people. All right? So it's not necessarily a good or a bad thing, but it's going to have the same effect on some people, okay? People with heart problems, we have to be careful about how much epinephrine we give them, okay? It also has positive effects in how the local anesthetic works, which is why we use it, okay? But that is an endogenous substance, and it can also be pumped into the body. When someone's going through a heart attack, they might actually pump epinephrine directly into their heart, okay? Interesting concept, all right? So it could either do the same thing as that endogenous substance, or it's going to block it, okay, to control or modulate a particular body process. This is very general. Same thing, or it modulates the amount of the effect, or it blocks it completely, right? When our body does anything, okay, so this is again very general, there's chemicals like the epinephrine, the adrenaline, that are called neurotransmitters that send signals along through our neurons, right? And then our neurons act on our individual tissues and our organs, and we're alive, right? They produce effects, right? So the endogenous substances or the drug help to send these signals along the axons, along the neurons, okay, through our body to produce an effect on the target organ, whatever that might be. And that's called a nerve action potential. Okay, you guys should remember about this. That's, again, I only read definitions when they're really important. The change in electrical potential associated with the passage of an impulse along the membrane of a muscle cell, a tissue cell of any kind, or a nerve cell. Okay, muscle makes you move, nerve cell creates feeling, okay, creates a response. So we're going to look at the action potential, and I'm going to really try again to have this work within the thing here. And if it doesn't, I'm going to go ahead and I have this saved on my desktop so I can play it. Oh, it's going to work.
Communication between two neurons begins when an electrical impulse called an action potential travels along the axon of a presynaptic neuron toward the axon terminal. The action potential cannot cross the synaptic space. When it reaches the axon terminal, it causes membranous sacs called vesicles to move toward the membrane of the axon terminal. The membrane of the vesicle fuses with the membrane of the axon terminal, enabling the vesicle to release its contents into the synaptic space. The molecules released from the vesicles are chemicals called neurotransmitters. They drift across the synaptic space and bind to special proteins called receptors on the postsynaptic neuron. The binding of a neurotransmitter to its receptor can trigger an action potential in the postsynaptic neuron. That electrical signal then moves toward the cell body of the postsynaptic neuron. Now that the neurotransmitter has relayed its message, it releases from the receptor into the synaptic space. Some of the neurotransmitter is degraded by enzymes in the synaptic space, and some of the neurotransmitter is carried back into the presynaptic neuron through transporter proteins. The neurotransmitter that is taken back up into the presynaptic neuron is then repackaged into vesicles that can be released the next time an action potential reaches the axon terminal. The entire process repeats each time an action potential reaches the axon terminal of the presynaptic neuron.
Okay, so that's very general. That's how our body works all the time. And drugs insert themselves into that process in a number of ways. So when we talk about the synapse, okay, between either two neurons or between the terminal neuron and the effector organ, okay, what we're trying to affect, that's what happens. So it might be that it's going to bind to the receptors. It might be that it breaks down those neurotransmitters in the synapse before they get sucked back in. There's a whole bunch, or keeps them there. There's a whole bunch of ways drugs can affect, that whole bodily process. But that's the basic thing. And you've probably seen something like that before, right? That's how it works. And we'll revisit that as we need to. And I do have these little animations posted for you if you want to go over them too. Okay. Moving on. Okay. So the drugs begin to work, okay, on the affected tissue or organ that we want them to work on at the synapse between that last nerve, if you will, or nerves, and the cell, okay, that we're hoping to have an effect on, okay, via those receptors we talked about. There's a bunch of different kinds of receptors, okay? There's a bunch of different kinds of receptors, but that's how the magic happens, okay? The effect that they have during that interaction, okay, they might interact with endogenous substances, our own, with drugs, or with both, okay? And the drugs can modulate how the endogenous substances work, or they can work in addition to the endogenous substances, okay? It's very general, okay? Because different drugs have different effects, okay? This will make actually a change, and there's another video that we'll see, a change in the shape of the area that's receiving the neurotransmitter, the receptor, the drug, whatever it might be, okay? Which allows the cells to produce their effect, okay? Or it can send another messenger to another neurotransmitter or another type of cell and then produce the effect. There's a whole bunch of ways that it happens. And I know when you're trying to understand this and really grasp it in your brain, it's very general, okay? So I just want you to know how that works, and then when we talk about specific drugs and how they work within that process, you'll have more an idea. You'll have this picture in your brain. In order to get to the receptors, okay, get into our body and then get to the receptors, the drugs have to go through all kinds of hoops, okay, if you will, and through biologic membranes just to get where we want them to work, okay? And depending on how you take the drug, how it's administered, and the effect that it has on your body, it happens in different ways. So we want it to have its therapeutic effect, and we know that it might also have an adverse effect. Because the drug, unfortunately, can't just get into the body, go right to where we want it, just do what it's supposed to do there, and then leave, right? It has other effects on other parts of the body. And the newer drugs, you notice there's one drug that does something, now there's a newer drug, and now there's a newer drug, and now there's a newer drug. Usually they try to make those new iterations, those new drugs, be more specific to what we want it to do without having the negative effects. If you have allergies, we know that the old allergy medication, no matter which one you took it and you were knocked out for the day, okay? It made you really, really drowsy. Whereas now they have ones that can get rid of the allergic effect, right? The histamine and all that kind of stuff, but it doesn't make you drowsy. That's an example of a more specific drug. So it has the effects on the allergic, all of the allergic reaction, but it doesn't affect the central nervous system as much and make you drowsy. So that's making the drug more specific. So we want it to have its therapeutic effect and minimize the adverse effects. When the drugs or the neurotransmitters get to those receptors, the better they fit there are different receptors. Remember I told you there's caffeine receptors, there's cannabinoid receptors, there's nicotine receptors, there's all kinds of receptors that we have, okay? Certain drugs, okay, that's why some drugs work doing one thing and some work to another, fit those receptors kind of like a lock and key. And the better they fit, the stronger their effect, okay, the stronger their effect. So if they're trying to do the same thing as the body, they're gonna look like the ones in the body. If they're trying to do something different than the body, okay, they might be stronger, they might be weaker. So there's this play between which are the stronger and which are the weaker. So when we talk about the neurotransmitter receptor interaction here, it's kind of similar to what we saw before. Think of this as the cell body, if you will, and this is the neurotransmitter. I love this. It's plugged into the central nervous system, right? Because the central nervous system controls everything. So coming from the CNS and across all of these different neurons, we get to the place, the synapse between the last neuron and the cell, if you will, where we have the receptors, okay, where that little magic is going to happen that we saw. And you can see this particular one like invaginates itself into the cell, and then it gets to the enzymes of the receptors within the cell. So they could be on the outside of the cell, they could be on the inside of the cell, and then elicit a response for both, okay? And we know that they can either mimic the body's effects or change it or block it in some way. So looking at the different ways that receptors fit, okay, see how that's kind of like a lock and key? So we have a receptor that has a certain shape to it, if you will, certain characteristics. And we can see here in B that we've got that beautiful lock and key effect. In C and in D, they don't quite fit as well, but they still might block something from happening. The better it fits, the stronger the bond. Most of the time, it's kind of a loose thing, and the bonds connect and they break, and they connect and they break, and they keep getting replaced, if you will. But again, the stronger that bond is, the more likely it's going to have that same effect or block that effect of the drug, okay? So we call this a stronger affinity, okay? Stronger affinity for the drug. You might say that two people that are friends have a strong affinity for each other, okay? This drug will have a stronger affinity for that receptor site if it has the same kind of characteristics or shape, okay? And it's going to bind to more receptors than a drug that has a weaker affinity, okay? That doesn't, quote, fit as well, okay? They're probably not shaped like these little keys and squares, but it gives you kind of an idea of how one might fit and have a better affinity than the other. When it combines with, the drug combines with the receptor, again, it can either enhance or inhibit the function of the cell or the affected tissue. So they're going to be either classified as agonists or antagonists. Really important to remember this. And I have some kind of funny ways to remember things as usual. Okay? So the agonist is the drug that has the affinity. So here's our friends, okay, and she's upset, okay? And you know your friend when you're upset, like, they don't, hopefully, sometimes they do. They don't usually say to you, oh, just get over it, okay? No, they say to you, gee, I know how you feel, okay? I know how you feel. They kind of move along with you. They help you through the process, okay? So these friends, your friend agonizes with you, and they sympathize, and they combine with you, and you'll both get sad together or whatever, okay? Or you both get happy together. Or they say, come on, let's go out for lunch, okay? And then you both get happy together. All right, that's your agonist, okay? It produces an effect, and the effect is going to be more similar to what the body would do. That's an agonist, okay, with its own endogenous substance, okay? It enhances the bodily process. Miranda asked me a good question at the beginning of the class, because she said, does an agonist always have a positive effect, and does an antagonist have a negative effect? Not necessarily, okay? We're just saying that the effect would be more similar. So let me give you an example again with the stuff we talked about. The epinephrine, right? It's the epinephrine we know works on the heart, okay? We'll learn about some of this next week, and makes your heart beat faster, okay? Makes your heart beat stronger and faster. That's a good thing if you're taking a run, okay? And that's why a lot of, like, quote, energy drinks have caffeine in them, right? Because they get you going. We've learned that some energy drinks are very negative. They have a lot of substances in there that can cause, you know, problems with the heart. So they enhance it. So that's a good thing. But remember, when you're sitting in a dental chair and you're already anxious and your heart is beating fast and you get epinephrine, it might produce that effect. And in that case, it's negative, right? But it's doing the same thing that the body's doing. Antagonists, okay? An antagonist, just like it says, when you antagonize something, okay? Okay, that's what I think of. I think of the middle school girls, 3 middle school girls, never a good thing, right? It's always, doesn't it always 2 against 1? A lot of the times, 2 against 1. I hated living through middle school. I hated having a daughter that was in middle school. Not a good time of life, okay? Good in some ways, but really negative in others, okay? So an antagonist, okay, works against or inhibits what the body might do. They can also be antagonistic of another drug, all right? And that's going to happen at that receptor site. There are different kinds. There's the one that competes, okay? There's the one that doesn't compete but modulates. And then there's one that physiologically antagonizes. And we'll go over the different ones. So a competitive one, just like it sounds, okay, blocks it. You're not getting in there, okay? I'm going to get in there, and I'm going to block what you're doing, okay? No, you're not going to have that effect on the body. Non-competitive doesn't try to bind to the same site, but it binds to different sites, and I'm over here, and I'm slowing you down, okay? Non-competitive, I'm not going to mess with your receptor, but I'm slowing you down. Physiologic has an affinity for a different receptor also, but it decreases the maximal effect by opposing. So if one of them binds to a different receptor and makes the heart beat faster, the other one binds to the receptor that's going to make the heart beat slower. Just very, very basic here. So it does an opposite effect. Yep, the physiologic antagonist binds to a different receptor, but does the opposite of what the endogenous substance would do. By doing the opposite to the body will have a different effect. So if one does, like, raises the blood pressure, the other one lowers the blood pressure. Just a basic example. Okay? Got it? So non-competitive and physiologic seem kind of the same, but they're not. Yes?
Wouldn't the non-competitive antagonist not allow the drug to work? Because if it binds to the different site, won't it change the shape?
It reduces the effect. It minimizes the effect.
Okay. So it wouldn't block it?
It is reducing the effect by doing some blockage, but it's not stopping it completely.
Okay.
Yep, because it binds to a different receptor, right? Because the other drug or the endogenous substance is still bound to that receptor, okay? But it's bound to a different one, and it's just modulating it and minimizing it.
Okay.
This is the generalization, okay?
Right.
Lots of drugs do different things, okay? And you may have, in those receptor sites, you may have an endogenous substance here, you might have an agonist here, and you might have an antagonist over here, okay? I can't simplify it any more than that, all right? You just kind of have to accept it. So when I say something is a competitive antagonist, you'll know what it means, blocking it. If I say it's non-competitive, it's doing something else, it's modulating it. If I say it's physiologic, right, it's going to push it and do an opposite effect, you'll know what I mean. All right? Yeah?
So if it does the opposite effect, it's not going to do
It's
Say
going
when
to
it's
stop
confined
that
to another-
tissue, okay, or that release of, substances. Again, it's very general. There's a million different things it can do. It's just going to do the opposite in this case on the tissue at that particular time. And remember, these effects don't last forever. Then these bonds are going to get broken and the body's going to go on and on, right? So if you're taking a drug that's going to dry up your saliva, so you're having oral surgery, you don't want to completely dry up your saliva for the rest of your life, right? At some point, the drug's going to get metabolized and go out of your body. Okay? So it wants to modulate it in a particular. So maybe you want a drug that slows down the amount of saliva but doesn't